Look around. Everything is spinning. Right now. The Earth beneath your feet is rotating once every 24 hours. The Moon is rotating as it orbits Earth. The Earth is orbiting the Sun. The Sun is rotating once every 25 days at the equator. The entire solar system is orbiting the center of the Milky Way galaxy. The galaxy itself is rotating once every 200 million years, and the galaxy is part of a cluster that's moving through space. Everything spins. Planets spin. Stars spin. Galaxies spin. Even black holes spin. Hurricanes spin. Tornadoes spin. Water going down a drain spins. Electrons spin, though that's different, and we'll get to that. The universe is full of rotation. Everywhere you look, things are turning. Why? What makes everything spin? Is it coincidence? Is there some cosmic force that sets things rotating? Or is there a deeper reason, something fundamental about how the universe works, that makes rotation inevitable? There is, and once you understand it, you'll see rotation everywhere, not as a strange phenomenon that needs explanation, but as the natural, inevitable consequence of basic physics. Rotation isn't mysterious, it's unavoidable. Let me show you why. Start with the most important law you've never heard of properly: conservation of angular momentum. You know about conservation of energy. Energy can't be created or destroyed, only transformed. You know about conservation of momentum. An object in motion stays in motion unless acted on by an external force. But angular momentum, that's the one that makes everything spin. And most people have never thought about it carefully. Angular momentum is rotational motion. It's momentum, but for spinning. Linear momentum is mass times velocity. Angular momentum is moment of inertia times angular velocity. The moment of inertia depends on how mass is distributed relative to the axis of rotation. Angular velocity is how fast something is spinning. And here's the critical law. In the absence of external torques, angular momentum is conserved. If something is spinning and nothing applies a twisting force to it, it keeps spinning at the same rate. Actually, that's not quite right. If the distribution of mass changes, the spinning rate changes to keep the total angular momentum constant. Think of an ice skater. Arms extended, spinning slowly. Pull the arms in, suddenly spinning much faster. Same angular momentum, but the moment of inertia decreased when the mass moved closer to the axis. So the angular velocity increased to compensate. The skater didn't do work to spin faster. The angular momentum was already there. Changing the mass distribution just changed how that momentum manifested. This is the key to understanding why everything spins. Angular momentum is conserved, and even the tiniest bit of rotation, amplified by gravitational collapse, becomes significant spin. Now let's go back, way back, to the early universe. Just after the Big Bang, matter is expanding outward, mostly hydrogen and helium. As the universe expands and cools, small variations in density appear. Quantum fluctuations from the early universe, amplified by inflation, create regions that are slightly denser than average and regions that are slightly less dense. The denser regions have slightly stronger gravity. They pull in nearby matter. Slowly at first, over millions of years, these density fluctuations grow. Matter accumulates. Gas clouds form. Huge clouds, light years across, containing the mass of millions or billions of stars worth of gas, just sitting there in space, slowly pulling together under their own gravity. Now here's the critical point. These gas clouds are not perfectly still. They can't be, because the universe is not perfectly uniform. Different parts of the cloud are moving at slightly different speeds, slightly different directions. There's always some net motion, some residual velocity, some small, random, arbitrary movement. It doesn't have to be much, a few meters per second of velocity difference across a cloud light years in size. Barely anything, a tiny drift. But it's there, it has to be there. Perfect stillness would require perfect symmetry. And the universe is not perfectly symmetric. There are always fluctuations, always variations, always some net motion. And that tiny motion has angular momentum. If one side of the cloud is moving slightly upward and the other side is moving slightly downward, the cloud has angular momentum. If one side is moving slightly left and the other slightly right, angular momentum. Any motion that's not perfectly radial, perfectly toward or away from the center, contributes to angular momentum. Now the cloud starts to collapse. Gravity pulls the gas inward. The cloud contracts, slowly at first, over millions of years. But as it contracts, something happens. The angular momentum is conserved, and as the cloud gets smaller, as the mass moves closer to the axis of rotation, the moment of inertia decreases. And to keep angular momentum constant, the angular velocity must increase. The cloud spins faster, much faster. The same angular momentum that was barely noticeable when the cloud was light years across becomes significant when the cloud is only billions of kilometers across. And as the cloud continues to contract, the spin rate continues to increase. Faster and faster. The initial tiny rotation amplified by gravitational collapse into rapid spin. This is why galaxies spin. This is why stars spin. This is why planets spin. Not because something set them spinning. Because they started with infinitesimal angular momentum, and gravity amplified it into observable rotation. Let's make this concrete. Imagine a gas cloud 1 light year across. That's about 10 trillion kilometers. And imagine this cloud has some small net rotation. Maybe one edge is moving at 1 meter per second relative to the other edge. That's walking speed, barely anything. The cloud is rotating, technically, but so slowly you'd never notice. One complete rotation would take trillions of years. Now gravity causes the cloud to collapse. It contracts down to the size of a solar system, say the size of Neptune's orbit, about 9 billion kilometers across. The cloud is now about 1 million times smaller in radius, and angular momentum is conserved, so the angular velocity increases by a factor of about 1 trillion. That walking speed difference becomes thousands of kilometers per second of rotational velocity. The cloud is now spinning noticeably, rapidly, obviously. This is not hypothetical. This is what happens. We've observed it. Collapsing gas clouds spin faster as they contract. Protostars spin. Protoplanetary disks spin. Young stars spin much faster than old stars because they haven't had time to slow down through magnetic braking and tidal interactions. The sun spins once every 25 days. That spin came from the angular momentum of the gas cloud that collapsed to form the solar system 4.5 billion years ago. The planets orbit the sun in the same direction the sun spins. That's not coincidence. They formed from the same rotating disk of material. The disk was rotating because the original cloud was rotating, and the original cloud was rotating because it had some tiny initial angular momentum that got amplified by collapse. Earth spins once every 24 hours. That spin also came from the angular momentum of the material that coalesced to form Earth. As dust and gas in the protoplanetary disk clumped together, the clumps had angular momentum. When they collided and merged, the angular momentum was conserved. The result is a spinning planet. Actually, Earth's current rotation rate is partly due to a giant impact. Early in Earth's history, a Mars-sized object collided with Earth. The debris from that collision formed the Moon. The impact also changed Earth's rotation rate. Before the impact, Earth might have been spinning faster or slower or at a different axis. The collision reset things. But the fact that Earth spins at all is because angular momentum was present in the material that formed Earth and was conserved through the formation process. The Moon spins, but it spins at exactly the rate it orbits Earth. 1 rotation per orbit. This is called tidal locking. It's not a coincidence. Tidal forces from Earth have slowed the Moon's rotation over billions of years until it became locked. The Moon still has angular momentum, but it's distributed between its spin and its orbit. The total is conserved. The individual components have changed due to tidal interactions, but the overall angular momentum of the Earth-Moon system is conserved. Galaxies spin. The Milky Way rotates once every 200 million years. That rotation came from the angular momentum of the gas clouds that collapsed to form the galaxy billions of years ago. Tiny fluctuations in the early universe created small net rotations in enormous clouds of gas. Gravity collapsed those clouds. The rotation amplified. The result is spinning galaxies. And not just spiral galaxies. Elliptical galaxies also have angular momentum. They don't have obvious rotation like spirals do, but the stars in elliptical galaxies are moving. Their velocities are not random. There's net angular momentum in the system. It's just distributed differently than in spiral galaxies. But it's there, because it has to be, because angular momentum is conserved, and any initial rotation, no matter how small, gets preserved and amplified. Black holes spin. Most black holes, possibly all black holes, have angular momentum. They're rotating. The space around a rotating black hole is dragged along with the rotation. This is called frame dragging. The rotation isn't optional. It's inherited from whatever collapsed to form the black hole. If a massive star collapses into a black hole, The star's angular momentum doesn't disappear. It's conserved. The black hole spins. And once a black hole is spinning, it never stops. There's no friction in space, no mechanism to remove angular momentum. The black hole spins forever. Hurricanes spin, tornadoes spin. Water draining from a sink spins, though not for the reason most people think. The Coriolis effect from Earth's rotation does influence large-scale atmospheric circulation, but it's far too weak to affect your sink. Water in your sink spins because of residual motion in the water and the shape of the drain, not because of Earth's rotation. But the principle is the same. Any small rotation gets amplified by the converging flow. Angular momentum is conserved. As water spirals inward toward the drain, it spins faster. Even at the quantum level, there's spin. Electrons have a property called spin. Spin up or spin down. But this isn't actual rotation. Electrons are point particles. They have no size. They can't rotate in the classical sense. Quantum spin is intrinsic angular momentum that doesn't come from motion. It's a fundamental property like charge or mass. The name is misleading, but it's called spin because it has the mathematical properties of angular momentum. It's quantized. It's conserved. It behaves like rotation in equations, even though it's not physical spinning. So why does everything spin? Because angular momentum is conserved, and because the universe started with small, random motions. Those motions had angular momentum, tiny amounts, barely measurable, but non-zero. And when gravity caused structures to collapse, when gas clouds contracted, when matter clumped together, the angular momentum was conserved. The collapse amplified the rotation. The tiny initial spin became significant, and the result is a universe full of spinning objects. There's no cosmic force making things spin. There's no fundamental law that requires rotation. It's an emergent property, a consequence of conservation laws and gravitational collapse. Start with any system that has even the tiniest angular momentum and let gravity pull it together. The system will spin faster as it contracts, unavoidably, inevitably. This is why planets orbit stars in the same plane. The protoplanetary disk was rotating. The material in the disk had angular momentum pointing in one direction. As the disk collapsed, that angular momentum was conserved. The planets formed in the plane of the disk. They orbit in the same direction because they formed from the same rotating material. This is why spiral galaxies have spiral arms. The galaxy is rotating. Stars in the disk orbit the galactic center. Density waves propagate through the disk. Stars enter and leave the spiral arms as they orbit. But the overall pattern persists because the galaxy is rotating. The spiral structure is a consequence of differential rotation. Inner regions orbit faster than outer regions. The result is a shearing effect that produces spiral patterns. This is why binary stars exist. Two stars orbiting each other. Common center of mass. The binary system has angular momentum. The stars orbit to conserve that angular momentum. If the stars were not orbiting, they would fall together and merge. The orbital motion balances the gravitational attraction. The system is stable because angular momentum is conserved. This is why accretion disks form around black holes and neutron stars. Matter falling toward a compact object has angular momentum. It can't fall straight in. It has to conserve angular momentum, so it spirals inward. Forming a disk, the disk rotates. Matter gradually loses angular momentum through friction and magnetic interactions. And as it loses angular momentum, it spirals closer, eventually falling into the black hole or onto the neutron star. But the disk exists because angular momentum prevents direct infall. This is why Saturn has rings. The rings are made of countless small particles. Each particle is orbiting Saturn. Each particle has angular momentum. The particles can't fall into Saturn because they're moving sideways too fast. The orbital velocity balances the gravitational pull. The result is a stable ring system. The rings are thin because collisions between particles dissipate energy, causing the particles to settle into a plane. But the angular momentum is conserved. The ring persists. Rotation is everywhere. It's built into the structure of the universe. Not because rotation is fundamental, because angular momentum is fundamental. Conservation of angular momentum is one of the deepest laws of physics. It emerges from the symmetry of space. If space is the same in all directions, if there's no preferred orientation, then angular momentum must be conserved. That's Noether's theorem. Symmetries imply conservation laws. Rotational symmetry of space implies conservation of angular momentum. And once you have conservation of angular momentum, Rotation is inevitable. Any system with even the smallest initial rotation will amplify that rotation as it contracts under gravity. The universe is not static. Structures form, gas clouds collapse, galaxies form, stars form, planets form. And every one of these processes involves gravitational collapse. And every gravitational collapse amplifies rotation. The result is a universe full of spinning objects. This is not an accident. This is not design. This is physics. Angular momentum is conserved. Gravity causes collapse. Collapse amplifies rotation. These are simple, well-understood physical principles. Applied across billions of years and trillions of star systems, they produce the spinning universe we observe. You might ask, where did the initial angular momentum come from? Why did the early universe have any rotation at all? Why wasn't everything perfectly symmetric, perfectly still? Because perfect symmetry is impossible. Quantum mechanics guarantees fluctuations. The early universe, at quantum scales, was seething with uncertainty. Tiny variations in density, in velocity, in every physical quantity. These fluctuations got amplified by cosmic inflation, stretched to astronomical scales. The quantum jitter of the early universe became the large-scale structure we see today. Galaxies, clusters, superclusters, all traced back to quantum fluctuations in the first fraction of a second after the Big Bang. And those fluctuations included velocity fluctuations, different regions moving at slightly different speeds, slightly different directions. That's angular momentum. Not much, but enough. Amplified by billions of years of gravitational collapse, those tiny initial fluctuations became the rotation we see everywhere. The universe doesn't spin as a whole. There's no preferred axis of rotation for the universe. But local regions spin, galaxies spin, stars spin, planets spin, each with its own axis, its own rate, inherited from the initial conditions of the gas cloud that collapsed to form it. The directions are random, the rates vary, but the fact that they spin is universal, because angular momentum is conserved, and collapse amplifies rotation. Now let's talk about what happens when rotation becomes extreme. Pulsars, neutron stars, the collapsed cores of massive stars, a star with the mass of the sun compressed into a sphere only 20 kilometers across, and rotating, fast, really fast. Some pulsars rotate hundreds of times per second. The entire star, with the mass of the sun, spinning faster than a kitchen blender. How is that possible? Angular momentum conservation. The original star was large, maybe 10 times the radius of the sun, rotating slowly, maybe once every few weeks, not particularly fast. But when the core collapsed, when it shrank by a factor of 100,000, the angular velocity increased by a factor of 10 billion. The slow rotation of a massive star became the incredibly rapid rotation of a neutron star. Same angular momentum, drastically different radius. The result is extreme spin. And those pulsars are incredibly stable clocks. The rotation rate changes very slowly over time. Some pulsars are more stable than atomic clocks. We can measure their rotation period to extraordinary precision. And we can watch how that period changes over years and decades. The pulsar is gradually slowing down, losing rotational energy. That energy goes into accelerating particles in the pulsar's magnetic field, creating the beams of radiation we detect. But the slowdown is predictable, measurable, a direct consequence of conservation of angular momentum and energy. This is why rotation matters. It's not just an interesting feature of astronomical objects, it's a fundamental aspect of how structures form and evolve. Angular momentum shapes galaxies. It determines how stars form. It affects how planets develop atmospheres and magnetic fields. It controls the evolution of binary systems. It governs the behavior of accretion disks around black holes. Rotation is everywhere because angular momentum is conserved. And understanding that conservation law is essential to understanding how the universe works. So look around. Everything is spinning. Earth spins, the sun spins, the galaxy spins. The entire universe is filled with rotation. Not because rotation is mysterious, because angular momentum is conserved and gravity amplifies small motions into large rotations. It's physics. Simple, beautiful, inevitable physics. And now you know. The universe spins because it has to, because conservation laws and gravitational collapse leave no other option. Rotation is not the exception, it's the rule. And any universe with gravity and conservation of angular momentum will be full of spinning objects, just like ours. That's the answer. Not mystical, not designed, inevitable. Everything spins because physics makes it unavoidable.